In this session, I'll be talking about different discrete probability distributions, just giving you a brief overview of each of these distributions and how do you really use them in R, right? If I really want to find out the probability function, how do I use it? If I want to find out cumulative distribution function, how do you use it? If I really want to find out the quantile corresponding to the value corresponding to a particular quantile, or if I want to generate some kind of random numbers associated with a particular distribution, how do I really use R to generate the data associated with each of these distributions? So we are going to take up the Bernoulli distribution, the binomial, geometric, hypergeometric, the Poisson distribution, negative binomial distribution, and finally we would just have a quick introduction to the Wilcoxon rank sum statistic, which would be used as an alternative to the t-test in our hypothesis testing sessions that we are going to look at later on. Now, generally, whether it is continuous or discrete, whatever are the distributions, in R, there are four set of functions. R is supporting four set of prefixes. So in some cases, you can give a prefix as a D. In some cases, it could be P, it could be Q, it could be R. So going with each one of them, if I am giving a prefix as P, it's like I am trying to find out the cumulative probability. So which is nothing but I will get the probability that X takes on values less than or equal to X. This is what is the P. So if I am talking about in the next slide, I'll quickly put up different kinds of distributions which the base R package is supporting. But the moment I put a P before that distribution, I'll get the cumulative probability distribution. Similarly, when I put a D, it is like a density function. In case of discrete variables, it's nothing but it is the probability of X is equal to X. That is what I can get through the usage of D. And when I'm using Q, probably take it as opposite of P. For what I will give probability as an input and it will compute this X as the output. So for what possible value of X, the probability of X less than or equal to X is equal to this much. That is what we are calling as the quantiles of the distribution. So probably you look at it as the inverse of the cumulative distribution, because the cumulative probability distribution will give me the probability of X less than or equal to X. But once I give the probability, it will the Q function will find out what is this value of X, where probability is of X less than or equal to X is that much. And when I want to randomly generate some kind of data set following a particular distribution, I'll prefix an R before it. So we'll try to use all these things as we move along in this session. So these are some set of functions which R supports, different kinds of distribution supported by R, but of course this table contains a mixture of both discrete as well as continuous distribution. So you find beta is a continuous, binom is a discrete, which we are going to take up in this session. Cauchy is continuous. So these things which are continuous, I'll deal in a session which is a separate session which is called as continuous probability distribution. So in this session on discrete, I'm only looking at the discrete session, discrete probability distributions itself. Yes, geometric is one discrete, hypergeometric is a discrete, log normal, logistic, negative binomial is discrete, normal is continuous, Poisson is discrete, Wilcoxon sign rank is discrete, the T is continuous, uniform is continuous, right? Bible is continuous, Wilcox rank sum is discrete. So I can very well talk about these discrete functions, and for all these functions, as we have clearly indicated, as I'm clearly telling you, all these four, probably if I want binomial distribution, when I say P binom, I will get probability, the binomial data is following a binomial distribution, I will get probability of x less than or equal to x. When I am using the d binom function, I will get probability of x equal to x. When I am using q binom as a function, I will give a probability, and based on that I will get that particular value of x where p of x less than or equal to x exists. And finally, when I am using R binom, I will be able to randomly generate numbers which are following a binomial distribution. So that's how you can prefix these PDQRs before each of these functions that are listed, which can give us the comfort level in terms of playing around with different kinds of distribution, right? Now, quickly looking at Bernoulli distribution. There's nothing much to talk about Bernoulli distribution because we are talking about one trial, right? We are doing an experiment once, and out of which there is a probability P where the success can occur. Success is what I'm calling as 1, and the remaining probability 1 minus P where a failure can occur. Failure means 0. So there are only two possible outcomes, success or failure. Generally success is denoted with 1 and failure is denoted with a 0. So if I am trying to find out the distribution that is underlying this kind of a binary response, I am calling it as a Bernoulli distribution. So there is, if I am talking about probability of x, right? So when I'm saying P is the probability of occurrence of an event, I'm putting it as P to the power of x, and failure is 1 minus P to the power 1 minus x. Now x could be only either 0 or 1. So if x is 0, then it is P to the power of 0 into 1 minus P. So overall lies as 1 minus P, which is failure. So the probability of getting 0 successes is 1 minus P. Probability of getting 1 success, if I am putting it P to the power of 1 into 1 minus P to the power 0. So which will end up as P. So the probability of success is P, probability of failure is 1 minus P. And expectation, which is nothing but 0 into P plus 1 into 1 minus P. So which is working out, so when we are talking about x times, right? Okay, 0 is 0 successes, the probability is 1 minus P, and 1 success, the probability is P. Overall the expected value is P. Similarly, when you are talking of expected value of x squared, the same logic I can use, 0 squared times 1 minus P plus 1 squared times 1 squared times P, which is again P. Expected value of x squared is also P. Expected value of x is also P. So variance is nothing but expected value of x squared minus expected value of x whole squared. So which becomes P into 1 minus P. So that's how we compute these things. There is nothing much to do in R associated with these, because it's not too many times a particular experiment is repeated. The same Bernoulli distribution will actually pave way for us to understand the binomial distribution in depth, right? The same experiment, instead of performing it once, if I perform it n number of times, right? The same. The probability of success is P, failure is 1 minus P, all else remaining the same. But if this experiment is performed instead of once, multiple number of times, that is where the Bernoulli distribution is giving rise to a binomial distribution. So it's when we are talking about a binomial distribution, still we are using the same context, p per x, 1 minus p to the power n 1 minus x. Instead of 1 minus x, we are talking of n minus x, because we are talking of x number of successes. So we are repeating a trial n number of times, out of which I am talking of x number of successes, which means n minus x number of failures. So p to the power of x, 1 minus p to the power n minus x. Now out of this n, any x could be successes. So that's where the number of ways in which x successes can occur out of n trials is nothing but ncx. This is the probability x successes can occur out of n trials, which is becoming ncx. So here the P is nothing but probability of success when you are doing one single trial. So n number of experiments being taken up, probability of success is P. So that's where the probability density function becomes ncx p power x 1 minus p to the power n minus x. So I can directly use binom as a function, right? We'll use that. But at the same time, if I really want just ncx value, I can use the choose function or factorial, because ncx is nothing but n factorial divided by n minus x factorial times x factorial. So either I can use the factorial function directly, or I can use choose. Choose can also give me, let's say if I want 8c3. So I can say choose 8 comma 3, which will give me 8c3 as 56, which is as good as saying factorial of 8, right? I can say factorial of 8 divided by 8 minus 3 factorial, which is 5 factorial into 3 factorial. So I'll say factorial of 5 multiplied by factorial of 3. So this is also coming out to be 56. So one way, if I want NCX, I can do that activity. But let's do the binomial distribution part, right? So we'll take up a quick numerical, right? I want to say the probability of success of occurrence of an event is, let's say, 0.2, right? I am doing an experiment 10 times. I really want to know what is the probability that I will get 3 successes, or probably I can even think of getting all number of successes. What is the probability that I will get 0 success, 1 success, etc. So let me take my x as 0 to 10. So x is 0 success, 1 success, 2 success, etc. And y, I'll take it as d binom, right? So how do I give d binom? If you look at, because I want to find out what is the probability of associated with each one of them when I am doing this experiment 10 times, when I am doing this trial 10 times. Now if you look at this d binom as a function, I am giving one x, which is 1 2 0 1 2 3 so on. The size is nothing but number of trials, so I am doing it 10 times, so the size is 10 trials, and probability is nothing but the probability of success on each trial, which is 0.2. So I have to give those as an input. So let me say I'm putting my y, right? I'm putting my y as d binom x for each x. So take my size as 10. So I am experimenting it 10 number of times. I am doing this trial 10 number of times. I want to find out how many times 0 successes come, how many times 1 success comes, and so on. And the probability of success is 0.2. So this is what I am calling as D binom. Right? Now I can very well have a plot of each one of them. Right? For each one I can very well have a separate plot. So you could clearly see the plot of x comma y. Or probably let me go with a bar plot directly. That would be better because there are only a few values. Bar plot of x comma y. So I could see that this is how the bar chart is coming out. The frequencies 0 to 1 is coming out this way, and the probabilities are coming out in this way. So let me look at the D binom. Let me see the y values just to see what the D binom is giving me. So these are the probability of getting 0 success is this much. Probability of getting 1 success is this much. 2 successes is this much. 3 successes is this much. 4 is this. So I could see that the probability of getting 2 successes is 1 success and 2 success are much higher, and the probability of getting more than those kind of successes is much lesser. So let me quickly look at, let me just take bar plot of y alone. Yeah, this is looking better. I'll take the bar plot of y. So these are the different kinds of probabilities. So you could see that in the initial stages the values are the probabilities are much higher, but after that the probabilities are slightly waning away. So that's how I'll generate the D binom. And for the same thing I could have used the P binom, right, which will give me the cumulative. So the cumulative means for x less than or equal to 0, I'll get it as 0.10. But x less than or equal to 1, I'll get it as 0.1 plus 0.26, 0.36. Then it becomes 0.66 and so on. So instead of using D binom, let me use P binom. Let me use P binom. Right? So on the same thing, let me put a lines y1. So I'll incorporate on the same graph, I'll put a line chart. Y1. So these are the values that are coming out for Y1. Okay, so even if I have to put lines, let me put it as x comma Y1. Okay, because we need to set the axis right, but otherwise what you could see is for different values of, let me just take plot x comma y. Plot x comma y, and if I put type equal to b, right, I am getting both the lines as well as point. But now I can very well say to this I want to add the lines x comma y1, but of course the axis is not set, so it is typically pointing it out only to this extent. So I should not define the axis initially, right? So if I don't define the axis initially, otherwise let me set the y limit when I'm doing the plot itself. Let me set the y limit to be between c0 comma 1. This would be better. Y limit I am setting it between 0 to 1, and instead of doing a plot, let me just do a plot of y alone, and let me not put this type B, let me directly call it as a bar plot. So this is how it is coming, and from here I want to add the lines x comma y1. Now this is how I can very well generate the bar plot of each of the densities, and corresponding to that I can very well bring in the cumulative distribution function also associated with this, right? Now the same way I can generate random numbers also. Let's say if you are talking of R binom, right? Now if you see R binom here, all you need to give is n, which is nothing but number of samples you want to generate. Let's say I want to generate 100 such samples. Size, which is talking about the number of trials, and probability. Three things. So when I say R binom, I am setting that I want 100 samples from a binomial distribution whose size, so number of trials, in each one the number of trials I want 10, and the probability of success I am taking it as 0.2, right? I am repeating this experiment 100 times. So I have got, these are the successes that are coming up in each aspect. So there are 3 success, 1 success, 1 success, 2 success, 0 success, etc. So this one I can very well take it as a table. This one I am taking it as a table. It gives me that there is a zero probability, there are 0 successes coming 9 times, 1 success is coming 32 times, 2 successes are coming 26 times. So you could see that the concentration of the successes is much higher in the initial phases if the probability of success is much lesser, and after that the probability of success is going down drastically, because you don't see a 6 here, 8, 9, 10. So you don't find all 10 successes at all in this kind of scenario, because the probability of getting all 10 successes is very rare, 0.0000 this much. So that is the reason when you are generating 100 random numbers, that kind of a success is not occurring at all. So that's how you can really plan your data, whether it is following a particular distribution. If you know that it is following a particular distribution, you can even simulate the values. And what you find is the mean of any binomial distribution. Now let's randomly generate the values, right? We have been randomly doing this. So let me assign it to a variable called data, right? Data bin, binomial distribution data. Randomly let me generate this data, right? So instead of 100, let me generate it to 1000, so that I can showcase all our calculations quite comfortably. Now I have generated 1000 data points, size is 10, probability is 0.2. So let me take the mean of this data bin. The data bin, I'll take the mean of it 1.93. So approximately equivalent to 2. Because we are theoretically saying that it is equal to NP. NP is nothing but number of trials that are performed in the experiment multiplied by 0.2, which is the probability of success. So I should get the mean as 2. When I am doing the simulation, I am getting it very close to 2. These two are not different. So which means this data is more or less following a binomial distribution. Of course, we have generated it from a binomial distribution itself. Then let me do the variance of data bin. So the variance is 1.5, and what we say is theoretically the variance is NP into 1 minus P. So 2 into 0.8, which is 1.6, and what we are getting is very close to that 1.6 itself. As the number of random samples keep increasing, I will get the values very much replicated closer to the theoretical numbers as such. Right, so the mean of the binomial distribution is NP, the variance is NP into 1 minus P, and because P is always between 0 and 1, you will find the variance is always lesser than the mean in case of binomial distribution. And we have already used all these D binom, P binom, Q binom. Okay, if I really want to find out what is that particular probability, so if I say I want a probability of 0.780%. Right, now let's use the Q binom to understand what it gives. So again I have to give the P, which is the probability. Right, what is the probability of success I really want, size, and the probability, all these three. So I'll give Q binom, let's say I want 0.8 probability, and size equal to 10 and probability equal to 0.2. So if I require P of x less than or equal to x, what it means is if I require P of x less than or equal to x is 0.8, what should be this value of x? It says it should be equal to 3. Now if you go back to your this table, this is 0.1 plus 0.26, 0.36, you look at it, you look at the P binom. 0.1, 0.37, 0.67, 0.87. So if I want 0.8, this is 0, probability of x less than or equal to 0. This is x less than or equal to 1, x less than or equal to 2, x less than or equal to 3. So it will give me that maximum value where x is lesser than or equal to x. So here it is giving me the output as 3. I need to have a minimum of 3 successes if I am talking about the probability of less than or equal to 3 successes is 80%. And R binom, we have seen we can randomly generate the numbers following a binomial distribution. So those are some of the things that we can be comfortable regarding the binomial distribution. You can create plots, bar charts, etc. You can understand the data more and more comfortably. Then the next distribution that we are looking at in this context is the geometric distribution. And let me tell you, the business application of the geometric distribution is I want to understand how many trials do I really need to wait to get the first success. How many times? What is the number of trials that I have to typically perform to get my first success? That is what I want to model, because the number of trials is a random variable here. Right, I want to get my first success. Number of attempts that I have to make to get my first success is what we are calling as a geometric distribution. It will follow a geometric distribution. So which means if I'm talking about getting the first success in xth trial, right, I'm getting my first success in xth trial, which means the previous x minus 1 trials are failures and the xth one is a success. So the probability wise, Okay, the probability of failure is 1 minus p, and because I had x minus 1 failures, the probability of x minus 1 failures is 1 minus p to the power x minus 1, and the probability of the success, which is one single success, is p. So that's where the geometric distribution will have a density function of p times 1 minus p to the power x minus 1. Now the same logics that we have used in case of binomial distribution, the same things I can use here as well. So all I need to give is the probability of success, and what it will give me, what is the probability that you will get the success in the first trial, in the second trial, in the third trial, and so on. What is the probability that you will get this success in the first trial, in the second trial, and third trial, so on. So let me take x is, let's say, 0 to 20. Right, I am taking the values of x 0 to 20. Y, I am calling it as dgeometric, where I am taking it as x, and here I just need to give the probability of success. The probability of success, let's say if I give it as 0.2, right? So the y's are, if you see here, okay, what the probability that you are getting as success in the first trial is this much. In the second trial itself is 0.36. So in the 0th trial, in the first trial, second trial, third trial, fourth trial, fifth trial, and so on up to 20th trial. These are the probabilities that you will get your success in each of these trials. And now when you are typically trying to plot the same, I'll take bar plot of I'll take the bar plot of y, setting y limit. I'll set the y limit as 0 to 1. I'm doing a bar plot of y, and now I can add the lines. So you could see here it's a kind of a decreasing, exponentially decreasing kind of a graph that we are getting out here. That is how, because when we are talking about some probability of success, initially the probabilities could be getting a success in one trial, this much, getting a success in two trials, getting a success in three trials, and if you are not getting successful, after that getting a success in the 10th trial, 12th trial, first success in 10th trial, 12th trial, means all the 11 are failures. It's a slightly a difficult kind of a scenario. And probably I can very well go with cumulative as well, where I'll go with PGM. I'll take x comma 0.2, and I'll add lines of x comma y1 to it. So the PGM is taking care of the density, the cumulative. So where all these, so this 0.2 plus this close to 0.2 is added, and that is what will become my cumulative out here, and so on. The values are added up to finally the cumulative distribution function working out to flattening out. Similarly, I can generate and let's say if I want to talk about success of 60%, right? If I'm looking at success confidence level of 60% or 80%, so what is the minimum interval that I can quote in this case? So I can very well talk about QGOM of 0.2. Right, when I am putting QGOM of 0.2, okay, QGOM, I require 0.8 is the percentage, right, 80% confidence, and the probability I'll set it as 0.2. So it says minimum of 7 trials, right? if I'm able to establish a success in seventh trial, then I can very well say if I have to be 80% confident that you will be successful, then I have to give you at least 7 trials, right? Then I'll be 80% confident that you will be successful. So that is what is typically given by my QGM, and I can very well randomly generate a geometric distribution values, right? If you are talking about RGM, you are giving n and probability, only two things. So I'll give RGM, I want 1000 observations that are following a geometric distribution where the probability of success is 0.2. And let's say I'll assign this to data geo, right? I'm assigning this to data geo. So if I simply type data geo, it will tell me how many. So in some cases, it is telling me that I'll be successful in 4 trials. I'll be successful in 1 trial. I'll be successful in 0 trials. I'll be successful in 2 trials, 5 trials, 11 trials, and so on. So these are the number of trials that I have to wait. Sorry, this is not in the nth trial. I have to wait for these many trials. So which means when I have to wait for 0 trials, means my first itself is a success. I have to wait for 1 trial, means my second is a success, and so on. So in some cases it's saying I have to wait for 22 trials also, which means, so there is some rare chance of getting that kind of a success. So I have to wait for 22 trials as well. So if I am simply looking at the table of data geo, it says, okay, out of 200 times, out of 1000 times, almost 192 times I don't need to wait at all. 155 times I'll be successful in my second attempt. 143 times I'll be successful in the third attempt, and probably 94 times I'll be successful in the fourth. But there are some very slim chances that I may have to wait even 40 times to get my first success. But that probability is very small. Now, if I am looking at the mean of this particular data geo, it is 4.1. And what the theoretically I am saying is the mean is nothing but 1 minus p by p. 1 minus 0.2 divided by 0.2. 0.8 by 0.2, which is 4. So on an average, I may have to wait for 4 trials. So on an average, I would be successful in the 5th trial. I may have to wait for 4 trials to become successful. That is what is being specified as a part of this mean. And if you are looking at the variance in this case, the variance is also much higher, 22, because variance comes out as 1 minus p by p squared. So 0.8 by 0.04, which actually works out as 20 theoretically, and even our data is coming closer to that. The close data, that the variance that is given by my data is around 22. So you'll find the tail is very long, right? If you are trying to do the plot of this table, right? If you are trying to do the plot of this table, you'll find that initially the values are much higher, the frequencies are much higher, but probably you find some kind of outliers. There are some extreme values that are lying out there. So I can, if I follow a geometric distribution, there is a very good chance that there could be a few extreme such kind of values that could be present in this data. So the tail is very long, and I can quite comfortably use all the 4 functions of R to understand what kind of data are typically following a geometric distribution, right? Now, once we are done with the geometric distribution, then the next important distribution that we need to understand in this context is the hypergeometric distribution, which also works on the similar lines. So it's also similar to a binomial distribution, whereas in the binomial distribution, we said that the trials are independent, right? So that is where we were saying that the sampling is typically done with replacement, because the same success can again and again occur. Whereas in case of hypergeometric, we are taking the similar concept but without replacement, right? It's as good as saying I'm having total of n elements, out of which I know that b of them are successes, right? I'm talking about I'm having n elements altogether, out of which b of them are successes. Now I am sampling out of this n, I am taking a sample of small n. Now I want to find out, when I am taking a sample of small n, what is the chance that x of them will be successful. So this is where, because I am sampling out small n out of capital N, so the number of ways in which I can sample small n out of capital N is NCN. Now when I am talking about successes, overall there are only b successes, out of which I require x of them to be picked, which can be done in BCX ways. And I am talking about, so when I am already out of this b which are successful, I am pulling only x of them. So out of the remaining n minus b that are there, I have to pull the remaining n minus x element. Now that is the reason the probability density function for a hypergeometric distribution lies as BCX, where B is the number of successes that are there in the original data. Then we are talking about X, which is the number of successes that I really want when I am pulling the stuff. Capital N talking about the total population size. So we have so many functions involving all these variables Q, B, R, N. Now here Q is typically the vectors, right? How many successes do I want? 0 success, 1 success, which is actually the X in this example. The X is what they are typically calling as Q in this binomial distribution function, right? In the R based function, the X is nothing but it's the Q. Then B is similar to the B out here, number of successes. R, we are talking about number of failures, which is nothing but n minus b, right? Wherever I am giving R, it is n minus b, which means I don't need to give n at all. Once I give my b and n minus b, that is what will constitute the overall population size. The overall population size is contributed by this, but based on this b, I will try to find out how many Q successes are there, etc. And what is the sample size that we are pulling out altogether. The small n is also one more thing that we are providing. And wherever the probability needs to be provided, right, because in Q hyper I have to give the probability, so I will give it as a value between 0 to 1. So let's try it out. And when I'm doing a random number generation from a hypergeometric distribution, I'm using another variable called m, which is what is the random sample that I have to really generate. So let's go with doing these functions, right? All right. So let's talk about x going between 0 to 10. I am taking the values of x going from 0 to 10. Now where I will set the b should be at least 10, right? Because out of the there are only 10 number of successes, so I need at least 10 out here. So I will find out this y as d hyper, wherein the first thing I have to give is q, which I will give it as x, so it should be either 0. So what is the probability that I will pull out 0 success, 1 success, 10 successes, etc. So overall there are 10 successes in the data, which is my b. Overall there are 20 failures in the data, and the sample size that I am pulling is also 10. Right, I am pulling a sample size of 10. There are 10 such kind of successes that are there in the data. So I really want to find out the values of y. So the values of y comes out like this. In all these cases the numbers are pretty small. Right now there are 30 elements altogether. Out of this 30 I am pulling out 10, and when I am pulling out 10, what is the probability that all 10 of them will be success itself? This is the probability, almost negligible. What is the probability that 9 of them will be a success? What is the probability that one of them is a success? Two of them is a success. Probably here it is looking much better. 0.18, 0.3. This is also 0.27. So the probability that two of them are successful, three of them are successful, four of them are successful, probably five of them are successful, these probabilities are much higher. But getting all 10 of them successful, the probability is much weaker. Right? So I can very well go with a plot, bar plot I will go associated with y. So this is how the probabilities are working out. Right, I can take the bar plot of y and I will set the y limit as 0 to 1. So this is how my bar plot is coming for this particular numerical, and I'll also set my cumulative also. So that's where I'll use p hyper, all else remaining the same. Whatever is the input that I'm giving to d hyper, the same input I'll give to p hyper, and I'll simply pull in x comma y1. So this is how my hypergeometric distribution cumulative density function is typically shaping up. So again the same thing, if I want to use my Q function, 80% success kind of stuff, if I have to be 80% confident, then I'll use my Q hyper, where I'm setting the 0.8 as the probability. Right, then I have to give all the other values, 10, 10, 20, 10. So 10 is the overall number of successes that are there, overall failures that are there, the sample size that I am picking. So which says I need to get at least I need to be get 4 successes at least. So that is what is corresponding to 0.8 here. We are talking about 4 successes. And if I have to generate R binom, talking about how many successes can be generated, right? For that I can use R binom, where I'll generate 1000 such samples. Right? I'll generate 1000 such samples, and all other things B, R, N will remain the same, 10, 20, 10. And this I can very well assign to data hype, unused argument. I can't give R binom. I have to give it as R hyper. Okay, so now let's look at data hype, how it is coming. So you could see that the values are 2, you will get 2 successes, 2 successes, 2 successes, 3, 4, 5, so on. So there are very rare that you are getting 10 successes or something. Even when you are taking the table of data hype, the table is saying that out of 1000 simulations, there are 4 where you have 0 successes, 56 where you have 1 success, 194 with 2 successes, 290 with 3 successes, 289 with 4 successes, and so on. So that's the kind of the table that is getting generated. Probably you can very well do a bar plot of this table also, which would reflect more or less this kind of a shape. And now when you are trying to find out the mean of this, when I am trying to find out the mean of this, what you will find is, as the sample size keeps increasing, right, especially if the total sample, instead of right now here we had it as only 30, but as this size keeps increasing and increasing, and even the B's and R's are also significantly higher, then I could find that the hypergeometric will actually approach a binomial distribution. Even in this case, if we start seeing, okay, so for the same data, right, so these are the probabilities that are coming up. The mean is 3.3 and the variance is 1.48. Now, if I am assuming the same data is coming from a binomial distribution, so if you look at B by N, right, B by N should approach P. So in this case, if I take B is 10, N is 30. So if I am taking P as 1 by 3, if I take P as 1 by 3, then R by N is 1 minus P, right? And N is 20, N is 30. Now I could, N is 30. So from here I could see that NP, no, N is 10 in this case, right? Small n, sample size is 10. Now if I am using NP as a as an indicator of the mean, I could have from the binomial distribution, it is 10 into 1 by 3, which is 3.33. But through the hypergeometric, I have got it as 3.34. It's almost approaching a binomial distribution. Even in the variance, we call it as NP into 1.1 minus P. So 10 into 1 by 3 into 2 by 3, which is 20 by 9, which is working out to 2 point something. Here I have got it as 1.48. If n is going much larger, I can very well approximate the binomial distribution in case of a multinomial distribution, because when the size is extremely small, extremely large, the sampling without replacement and sampling with replacement, I hardly see any kind of a big difference between these two processes. So I can very well assume the sampling with replacement and sampling without replacement to be more or less one and the same. So this is what is where we call, as the size of the population keeps increasing drastically, keeps approaching to infinite, I can very well use the binomial distribution as a limiting case of the hypergeometric distribution. Alright. Now from hypergeometric, we will move to another important distribution which is very heavily used in the discrete probability world, which is the Poisson distribution. So I will be using Poisson distribution for describing the count data, right? How many, again, successes itself. Generally, we find Poisson distribution to be a limiting distribution to a binomial distribution. In the binomial distribution, if n is very large, probability of success is very small, and the product of these two is more or less constant, then I will use a Poisson distribution as a limiting case of binomial distribution. It is one specific distribution where the variance and mean, both of them are one and the same, lambda. So for those kind of distributions where the mean and the variance is the same, I can very well use the Poisson distribution. The density function for this comes out as e to the power of minus lambda into lambda to the power x by x factorial, right? So when I'm performing an experiment n number of times and I want x number of successes, right? Here I'm not talking about an experiment being performed n number of times. I'm only defining np, which is on an average what is the success. I'm defining this lambda, which is talking about on an average what is the number of successes, and based on that we want to find out what is the probability that we are getting at least one success, two successes, so on. So lambda is the mean number of successes, and based on that I'm trying to find out what is the probability of each of the number of successes. So we can very well use the same set of functions, right? If you want, you can very well p-poise. When we are talking about p-poise, I have to give two inputs, x and lambda. X is the number of successes we are talking about, and lambda is what is the mean of success, what is the average success value. So let me put x is 0 to 10 and y, let me call it as d-poise. So I'll use the Poisson distribution values for each value of x, where the lambda I'm setting it as 4. If my lambda is 4, I want to find out what is the probability of getting 0 success, 1 success, 2 success, 5 success, 10 success, so on. So I can very well plot the same, because this lambda is the average number of successes. So there is a chance that I will get more number of successes also. Here we are not talking about n number of trials, because n is approaching infinity here, right? That is what is the Poisson distribution all about. Now I am taking a bar plot of y. So this is how I am getting the bar plot of y. Probably I can very well set the y limit I'll set it as 0 to 1, and y1 I can very well call it as cumulative, so where I'll take it as p-poise with x comma 4, and I'll add lines x comma y1. So this is how the Poisson distribution's cumulative distribution function is going to come out. And probably I can very well see, if I want 0.8 confidence level, what should be the successes, what should be the number of successes, then I can very well use the q-poise. Similarly, I can generate r-poise giving n number of samples and lambda value. So I can very well generate r-poise, which will randomly generate the number of successes. So I'll generate some 1000 successes where my lambda value is 4, right? And these things, let me take it into data poise as a variable. So when I'm looking at my data poise, okay, so I'll take the direct table of data points, right? Unnecessarily publishing the data. I'll take the table of data points. It says that, so when I repeated this experiment 1000 times, it has generated 29 zeros, 78 ones, 136 twos, 209 threes, and so on. So you could see that in the middle, especially around 4, 3, 4 kind of values, the probabilities, the number of values that are generated are higher. But a few extremes are also generated. Means there are 3 out of 1000 chances where I can get 11 successes also when your on an average success is 4 if it is following a Poisson distribution. And if you look at the mean of data points is coming out to be 3.93, which is very much equivalent to 4. And variance also, if I look at data points, it's also 4.2. This is also around 4. So this is the kind of a data where the mean and the variance are more or less equal. So that's one specific property that we are talking about, a Poisson distribution. So there are a couple of areas where you'll use them heavily in statistics. So understanding is very much important. Lot of times when we are using generalized linear models, especially for count related data, right, where we have something called Poisson regression itself, when I am doing the counting of the data, when I am doing a modeling for count related data, I'll use this specific feature called Poisson regression. So where the Poisson distribution is coming in handy. So the frequency distribution of counts of very rare but independent event, right? I mean the probability of occurrence is very small, but there are n number of such trials which I am performing where the probability of success is very small. Then if I have to model the success, then I can, instead of using a binomial distribution, I can very well use the limiting case of binomial distribution, which is the Poisson distribution itself. Alright. Then the next thing that we are looking at is a negative binomial distribution, which is otherwise called as the general case of geometric distribution. Because in the geometric distribution, we said the waiting time or the number of trials that I have to wait to get my first success, right? The number of trials that I have to wait to get my first success. Whereas in the negative binomial, we are talking about to get the rth success, not the first success. It could be 4th or 5th or 10th success. So I'm talking about how much is my waiting time to get the rth success. So if I have to get my rth success in xth trial, then I should have got r minus 1 successes in x minus 1 trials. So getting r minus 1 successes in x minus 1 trials is p to the power of r minus 1 and 1 minus p to the power of x minus 1 minus r plus 1 x minus r. And now I am getting in the xth trial there is a success, so the p. So overall it becomes x minus 1 c r minus 1 p to the power of r 1 minus p to the power x minus r. So this is the density function that is associated with the negative binomial. The same set of logic you can use the dn binom, rn binom, pn binom. There is no point in repeating the same set of activities. It's just you can treat it as a generalized form of the geometric distribution. So instead of taking the first success, we are specifying the r, an additional parameter we are specifying, which is the r, because we want to look at the rth success in this case instead of the first success or the second success. Instead of the first success, we are looking at the rth success, whereas in geometric by default it takes the first success itself. So that's a small difference that is existing between the negative binomial distribution and the geometric distribution. Alright. Then one more important distribution that we can look at here, used a lot when we are doing the comparison between the distributions. right? Comparison of a location parameter from a sample, location parameter associated with a sample. If the data is more and more closer to normal, then I could have used a t-test. But wherever I can't use a t-test, I have to depend on the Wilcoxon rank sum test itself. So it is the discrete equivalent of the t-distribution, which is used in a lot of applications. So it is returning the exact probability at a discrete values of q. So generally it is computed based on the ranks, right? The detailed process of it I have explained it in my other video of computing the Wilcoxon, performing a Wilcoxon rank sum test on one sample data and two sample data. But otherwise, just like the other distributions, you can use the Q Wilcox, D Wilcox, P Wilcox, all these kinds of functions, and even you can generate random number of trials also. You can generate random numbers also associated with the data following a Wilcoxon distribution. So when you are talking about usage in R, there are so many practical applications which are discrete distributions. We just need to understand which of these different kinds of distributions is my data following, so that once I am able to model my data following this kind of a distribution, it's like I have generalized from specific to a general, and which can help me in making conclusions or even making predictions at a future period of time. And even I can do a lot of simulations. The moment I know from my historical data, I'm able to generalize it saying this particular data is following this particular kind of a distribution with these parameters, then it's like I have generalized it. Now once I have generalized it, I can use the random number generators to generate futuristic values for following this particular distribution, and I can make so many probabilistic statements based on the data out of following this particular distribution. That's one of the prime reasons we would try to map our data to a particular distribution, so that I can make conclusions, inferences, and even predictions based on that. So the overview of all these distributions are primarily meant for us to understand how do I really associate the data to what kind of a distribution. Alright. So this is where I wanted to cover all these basic discrete probability distributions. If you have any further queries regarding any of these, you can get back to me by giving me a call on the number that I have provided below, or you can even send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.